Okay, we're talking about second order linear ODEs, and we saw that the constant coefficient case, which was this, the homogeneous constant coefficient case, which was this basically, was solvable, right? You could get y1, y2 by just putting e to the power of RT into this and then solving for R, the quadratic equation, getting two solutions y1, y2, y1 being e to the power of R1t, y2 being e to the power of R2t. Then you get two linearly independent solutions when R1 is not equal to R2. Remember, we said for R1 equal to R2 becomes a little complex. We'll come to that condition a little bit later on today. And if you do that, then you presumably get a general solution to this equation, which is C1 y1 plus C2 y2, and then we said, so y, we call this the y h, this is C1 e to the power of R1t plus C2 e to the power of R2t, this is an R1, okay, and this was the general solution. You could put the initial conditions or boundary conditions or whatever you have into this, and then you can get y as a function of t. You can solve this problem. And then we also went to the non-homogeneous case, or what we call the forced case from the oscillator point of view, that spring mass thing that I drew briefly, where you had a forcing. This was the forcing case. So we called this 2, and I think we called this 1. And we were looking at a way to solve this, and I told you that you can use for the particular solution. Remember, we said general solution is yh plus yp. Yp is a particular solution that solves this. And then I said you can use a yp that looks like this, put it back in to the equation, and then you see what to do with u1, u2. And then towards the end, I also mentioned that there is one equation but two unknowns, but you can put another auxiliary condition to get a unique u1, u2. So we'll go over those steps again a little bit more carefully now. And basically that should tell you that any constant coefficient second order linear ODE is solvable. Okay, you should have no issues in solving it. If you can reduce any more complicated situation to this or this, you're done. Okay. So before we go ahead, let me just rework this thing, which was done quite fast at the end of the previous session. So in case you didn't follow at that point, I'll just go over it again. So if I do dyp by dt, this was u1 prime y1 plus u1 y1 prime plus u2 prime y2 plus u2 y2 prime. And remember, when we put this to the second derivative and so on, and we put this into the equation, we saw that these terms y1 prime y2 prime, these terms actually went off because y1 y2 solve they solve 2. So then we put an auxiliary condition. We said that these two terms should sum up to 0, and I mentioned why we have to do that, because we, at the end of all this, we will end up only with one equation for the two unknowns u1 and u2. So we put this as a second condition, okay, in which case u2 prime is minus u1 prime y1 by y2. Okay, so we'll call this number 3. And then we go ahead. Now, since these two terms sum to 0, dyp dt is only this, and so if we continue to do the second derivative, you will get u1 prime yp prime plus u1 y1 double prime, two terms from this, two terms from this, you get u2 prime y2 prime plus u2 y2 double prime. And if you take this and add it up with a p naught or whatever to get this, so you put this and this and this into equation 1, then you will get something that looks like the following. You will get u1 prime y1 prime, this again y1 double prime y2 double prime, work it out, it's fine, plus u1 y1 double prime plus u2 prime y2 prime plus u2. It's just algebra. There is nothing fundamentally insightful about this is just doing algebra and yeah, just have to make sure that you don't miss any terms. That's all there is to it. So then P naught times u1 y1 prime plus u2 y2 prime plus q naught times u1 y1 2 is equal to f. That's what equation 1 was, and so we put all this stuff there. This is now equation 1, this guy. And you notice already that like we did last time towards the end, if you take out u common from this term, this term, this term, these guys will cancel because y1, remember, solves 2. Similarly, the sum this will also cancel because u2 also, so y2 also solves 2. So what you're left with basically is this, which is u1 prime y1 prime plus u2 prime y2 prime is equal to f. Okay, that's all you're left with. So this, let's call this equation 4. Okay, so we have two unknowns, y1, u1, u2, and we're left now with two equations 3 and 4 from which to determine them. Good. So why don't we determine them from here? Now clearly these are algebraic equations, they're not even differential equations, okay, because both contain u1 prime and u2 prime and not u1 and u2 themselves, right? So that's good. And we know all about algebraic equations from our study of linear algebra, presumably. So you can probably close your eyes and solve this system. So I'm going to put 3 in 4, and I will get u1 prime y1 prime plus u2 prime is now this guy with a negative sign minus u1 prime y1 by y2 is equal to times y2 prime is equal to f, okay, f of t. So if I take out u1 prime common to both, then y1 prime y2 minus y2 prime y1, which is this, is equal to f times y2. So now I have u1 prime is f y2 divided by y1 prime y2 minus y2 prime y1. Okay, and from equation 3, which was just this, I have u2 prime is minus y1 by y2 times this, so that will be minus f y1 by y1 prime y2 minus y2 prime y1. Okay, so I have these two. I've solved the problem, right? I've got u1 prime. Now the only thing I have to do is I have to do an integral of this times dt. Everything on the right hand side is a function of t. Remember, f is f of t, y2 is y2 of t, which is already known, solves the homogeneous problem, y1, y2, so on. So I only have to integrate and I'll get u1 and u2. Okay, so this scheme works. Gives you a unique value for u1, unique value for unique functional form for u1, unique functional form for u2. Okay. So what that tells us is first of all, you probably want to look at these two expressions for reasonably long amount of time and make sure that whatever is hidden here is clear. Okay, first let me bring that out. So this I can write as, if I take a negative sign out, minus integral fy2 dt divided by, if I take a negative sign out, I'll flip the order of these two. So I'll get y1 y2 prime minus y2 y1 prime. This is the Wronskian. Okay, let me call the Wronskian w of t. I'm going to write w of y1 y2, doesn't matter, you can call it w of t because the function of t at the end, right? Because y1 y2 are function of t. So this w was the Wronskian. Okay, and likewise u2, if I put this negative sign inside here, again it will flip, it will be f y1 dt by w of y1 y2. Okay, so the Wronskian turns up, right? Wronskian is important. You can already see that it's important because it's turning up seemingly out of nowhere, we started with this y is equal to u1, yp is u1, y1 plus u2, y2, whatever, and all of a sudden we've ended up with a Wronskian, right? So you see the Wronskian actually has a very important role to play. Now what is that role? The role is basically in making sure that the technique works. When will the technique fail? First of all, this entire scheme, u1, u2 are two arbitrary functions. I can write an unknown function in terms of two arbitrary functions as long as I know I have two equations to solve for the two arbitrary functions, which is what we have done. But when will it fail? It will only fail when the denominator goes to 0, because when the denominator goes to 0, this guy is going to infinity and this guy is also simultaneously going to go to infinity. So you have two functions that are not bounded, not defined, and so this entire scheme will break down. Okay, that's the only situation in which it will break down. But that will never happen because y1 and y2 are linearly independent. So the Wronskian is useful because it makes sure that this procedure always works. As long as you give it two y1 and y2, two linearly independent y1s and y2s, this procedure will always work. Okay, and it will always work, of course, only for second order equations of this form, because you can put them in and stuff will cancel and so on. Otherwise, if you had a nonlinear term, you are completely in trouble. Okay, so you can do this, and you can write down now the general solution is u1 y1 plus u2 y2, and the homogeneous problem solution is again as before. C1, C2 are constants that come from the initial conditions of the boundary conditions, and so the general solution to the equation 1 is yh, the homogeneous, plus yp. Yh is also sometimes called yc, complementary solution, which is same thing. This is called the complementary equation complementary to this and whatnot. Okay, so it's just a question of nomenclature. Okay, so if somebody gives you this equation, you find the solution of this equation, build them up like this, write this in this form, and then u1 and u2 will be given by this. Okay, simple enough. So you can solve in general this equation for any arbitrary p, any arbitrary q p naught, any arbitrary q naught, and any arbitrary f. Okay, I can give you any arbitrary f, you just have to put it into the integral and you can solve for it. So we have a way to write down the solution. Good. So that really is the analog of the 1D integration factor stuff that we did, right? I mean, 1D integration factor was good because it gave us again y as a function of some integral of the coefficients that are there. In this case, the coefficients are constant, and this is the only case where you can get an analog of the 1D linear integration factor thing. Okay, this is as far as you're going to go. Okay. Okay, I hope this is clear. Good. Now, before we proceed, let me make a couple of comments about this Wronskian. This Wronskian is sort of critical to this entire enterprise, of course. It seems to turn up, like I said, from nowhere. So let's talk about this Wronskian a little bit. Where does Wronskian come from? Why is the Wronskian a measure of linear independence? I never told you that at the start, because I wanted to go through this procedure and see that the Wronskian is useful, is a useful thing to talk about before we say anything significantly deep about it. But why is W of y1, y2 useful? Okay, and the reason is the following. If you had a vector, let's say I had a two-dimensional vector space, we call this V. V is a two-dimensional vector space. So to get a basis for V, I need two linearly independent vectors, alpha 1, let's say, and alpha 2, or let me call it V1, V2, it's better, V1, V2. Okay. And when you say V1 and V2 are linearly independent, you say they're linearly independent if you can get V1, C1, V1 plus C2, V2 is equal to 0. If there exists C1 and C2 such that V1 and V2 obey this relationship, then they're linearly dependent. So which means you can take it to the right hand side, right? V2 is some number, right? That is C2 by V2 times V1, C1 times V1. And this is a number. C2 is a constant, C1 is a constant, non-zero presumably, and then you can write V2 in terms of V1, and it's not linearly independent, right? Now, if you extend this idea to functions, what do you have? Let's say I have y1 of t, y2 of t. Okay, there are two functions, two linearly independent functions. Okay, and I asked the question, under what conditions are these two functions linearly independent? You can do the same thing that we did here. Okay, so you can write down c1 y1 of t plus c2 y2 of t equals 0. Presumably, if you can find two non-zero values of c1, c2, then it will be linearly dependent. If you can't do that, if c1 and c2 are 0, when this is true, then they are linearly independent. Yeah, so let's make sure that this definition is okay. But now, in addition to this, you also need a constraint on the derivatives. So you take a derivative of this, and you will get this. Okay, if I just take a derivative of the first one, I'm going to get the second one. Why do we need this? Well, y1 and y2 are arbitrary functions, and they're not just arbitrary functions, but in our context, okay, they're arbitrary functions that obey a second order differential equation like this, homogeneous, right? And so the loosely speaking degrees of freedom that you have available to you are y, the value of y or y1 or y2 at t equals some t naught, let's say, and dy by dt. Okay, those are the two degrees of freedom you have available. If you take the second derivative, it's constrained by this equation. Second derivative is given by this, so it's not a degree of freedom that you can vary arbitrarily. So you can vary y arbitrarily, you can vary dy by dt also arbitrarily. Similarly for y1 and for both y1 and y2, but you can't do the second derivative because it obeys the second order ODE. Okay, so now you have those two equations, which is the analog of this guy for the linear vector space, for standard linear vector space. Okay. Now I can write this in matrix form, of course. I can write this as m times c1 c2 is equal to 0. Okay. This is just this. If I need linear independence, then c1 and c2 must both be 0. Okay. If c1 and c2 are not both 0, then I can write y1 in terms of y2. Okay. In order for c1 and c2 to both be 0, I should be able to multiply both sides of this equation by the inverse of m. Okay. So if I do m inverse m here, I do m inverse m here, m inverse of this is presumably 0 vector is going to give you 0, m inverse m will give you identity. So c1 c2 will give you 0 0, that is when they are linearly independent, right? Same energy as here, but now you have a matrix 2 by 2. If this is the case, if I am able to do this, then that means m is invertible, because I am writing an inverse, it needs to be invertible. If m is invertible, then determinant of m is non-zero. Okay, that's the only time I can pre-multiply with this, and then I can get c1 equals 0, c2 equals 0. So again, I have these two equations. I've written it down in terms of, let me actually maybe write down the m explicitly. I've written it down, I've taken a derivative because these are the loosely speaking degrees of freedom. We'll understand what that means when we talk about this phase space stuff in more detail a little bit. But for now, okay, loosely you understand that these are like the only two things you can vary in the system, because if you take the next derivative, you're already there, differential equation of second order. And so I have set up these two systems, these two equations, and I said that if you can find non-zero c1 and c2 such that both of them are simultaneously satisfied, then y1 and y2 are not linearly independent. They're dependent on each other, right? Just like the vector space case. And I've just recast this in the form of this. So this is y1, this is y2, this is dy1 by dt, this is dy2 by dt. Okay, that's what m is. I've just written it in that form. So I have m times c1 c2. If y1 and y2 have to be linearly independent, then I should be able to invert m, multiply both sides by m inverse, and then I will get c1 c2. If I multiply right hand side by m inverse, I'm going to get only the 0 column vector again, because some matrix times the 0 vector will give you the 0 vector. So I'll get c1 equals 0, c2 equals 0. Okay, but that means m must be invertible. if m is invertible, then it implies the determinant of m is non-zero. Okay, so for these two guys to be linearly independent, determinant of m must be non-zero. So what is the determinant of m? Determinant of m is y1 y2 prime minus y2 y1 prime. This is just the Wronskian. W of y1 y2. Now this idea can be extended beyond equation 2. This, remember, y1 y2 were solutions of homogeneous problem. They can be extended beyond equation 2, because the only thing I need are two linearly independent solutions. Two linearly independent solutions to any linear second order ODE. I can replace P of t by some arbitrary thing, replace Q of t by some arbitrary thing, some function of t. If I can find two solutions, I can use the Wronskian again to determine if they are linearly independent, again using the same logic. Okay, so this idea applies irrespective of whether we are talking about equation 2, which is constant coefficients, or any other arbitrary equation. Okay, so it's a general construct. Wronskian is a general construct. Wronskian is also important from another point of view, which is the following. Now, if I am given y1, one of the y's that obeys the homogeneous equation, then can I generate y2 obeying 2 such that w of y1 y2 is not equal to 0. Okay, so this is the sort of next level of generalization. If somebody just came and gave me y1, okay, for this case constant coefficients we know how to solve, so we know how to get y1 y2 simultaneously. But if somebody gave me y1 and then they wanted me to find a y2 that was linearly independent of y1, then the next question I can ask is, can I generate a y2 that obeys the original equation such that the Wronskian is not equal to 0? Okay, why does this question, this seems like a very strange question, why will it matter in this case, okay, in the context of this case? It will matter because of one case that I have just conveniently kept aside till now, okay, which is the following. So if you take 2 and put y equals e power RT, then you are going to get an equation that looks like this: r square plus p naught r plus q naught is equal to 0, and then you will solve quadratic equation. If it so happens that p naught square is equal to 4 q naught, for whatever reason, then the two solutions will become the same by 2 minus p naught by 2. Okay, the quadratic equation will have equal roots. Now we are in trouble. Okay, why are we in trouble? Because in this situation, the e power r1t and the e power r2t, if you calculate the Wronskian of this guy, you will get it equal to 0. r1 is equal to r2, right? So if you calculate the Wronskian, you will get e to the power of rt, e to the power of rt. Take derivative r e to the power of rt, r e to the power of rt, it will give you 0. So we are in trouble. So now the question that I just asked, if I gave you y1, one solution that obeyed this equation, can I generate a second solution such that the Wronskian becomes non-zero? If that happens, then I know that the second solution is linearly independent of the first. And so then I can write y1, y2, c1, y1, c2, y2, u1, y1, u2, y2, the usual stuff. Okay, then I can solve the problem, right? And there's a way to do this. It's called the method of reduction of order. Okay, let me write this down explicitly. So given y1 of t obeys 2, get y2 of t obeys 2 such that w of y1 y2 is non-zero. Okay. Good. So if this is done, like I said, using this technique called method of right here. Of order, it's basically the same as what we did to get yp from yh. Okay, remember what we do there? We had yh as c1 y1 plus c2 y2, and then we just replace c1 and c2 by some unknown functions. Okay, and then we solved. So what we'll do now is we'll write y2 is some unknown function of t times y1 of t, some arbitrary function, does not matter. Whatever y2 is, I will divide it by y1 and then I'll call that function nu. Can do that, right? If I do this, I can take this fellow, calculate the derivatives, y2 prime y1 plus nu times y1 prime, calculate second derivative, nu double prime y1 plus nu prime y1 prime, the 2 from here plus nu times y1 double prime. Okay. And I can put this back into the original equation, exactly like we did for yh, but now we are doing it with just one unknown function instead of two. So notice now we don't have to put an additional condition on nu like we had to do for u1, u2, because there we had 2 and 1. Okay, whatever. Okay, good. So if I put this here, I'm going to get nu double prime y1 plus 2 nu prime y1 prime plus nu y1 double prime plus p naught times nu prime y1 plus nu y1 prime plus q naught nu y1 is equal to 0, homogeneous equation, right? I am looking for another solution that obeys the homogeneous equation 2. So now if you look at this for some finite amount of time, you will realize that this term and this term have nu commons. If I take out nu common, I will get y1 double prime plus p0 y1 prime plus q0 y1, which is 0 because y1 obeys this equation. So I will get rid of that. Okay. So the only thing I am left with is this. And remember, given y1, so y1 is known, right? It's a known function of t. Let's keep that in mind. Write it this way. I have to solve this equation to get nu. Okay, write that down here. This is okay. Now you notice y1 is a known function. Y1, because it's already given to you, you're trying to get another y2 that is linearly independent of y1. So y1 is a known function now. Okay, y1 prime is obviously known because you know y1 you can take a derivative. It's the easiest thing you can do in this course. And so what you will now do is you will realize that if I divide throughout by y1, let me divide throughout by y1. I will get nu double prime plus p naught plus 2 y1 prime by y1 times nu prime is equal to 0. Okay, there we go. This is a first order ODE for nu prime. So if I just change definition, I call w is equal to nu prime. Then this equation basically is dw by dt plus p naught plus 2 y1 prime by y1 times w is equal to 0. Okay, so I am done. It's a first order linear ODE, right? Linear because this is some arbitrary function of t, p naught is known, y1 of t is given, so you can calculate this is a function of t. But you just cross multiply and integrate. Okay, so it's easy enough to do. If you go ahead and do that, then you will get 1 by w dw, which will let me do it, because minus p0 plus 2 y1 prime by y1 times this. So I'm going to just take dt here, integrate both sides. I'm going to get log of w is equal to this. So I'm going to get w is equal to some constant, you don't care what it is, times exponential of minus integral p naught Okay. So I can write this out. So the first term, of course, is integral p naught dt, that is just t. So this will be constant times exponential of minus p naught t minus the second term, which is 2 y1 prime by y1. I can write, if I take d by dt of ln y1, I'll get 1 by y1 dy y1 by dt. Yeah, that's what this is, and that's what I have here. So then if I multiply both sides by 2, I'm going to get of ln y1 square, presumably. And so I can replace 2 y1 prime by y1 by d by dt of ln of y1 square. So then I'm going to get integral within the exponential, integral d by dt of ln y1 square dt. That will just give me ln of y1 square. Okay, don't worry about the constant, we'll leave the constant out for now, but okay, whatever. Okay, and this gives us w is equal to, I'll leave the constant out, exponential minus p0 t times exponential of log of this will just give me this, yeah, with in the denominator. Why is that? Because this minus I can put in here and make this plus and make this ln of 1 by y1 square. Exponential of ln of 1 by y1 square is just 1 by y1 square. Okay, so that is done. So I have w. I only know now that w is nu prime. So this I can just replace with nu prime. And so all I have to do now to get nu is to do integral this dt. Okay, so that's the method of reduction of order. So I can write down the form like this, go through this entire procedure, again fairly standard procedure, and then you will arrive at an expression for nu in terms of p0 whatever y0 square. So the right hand side is a known function. Yeah, so you should be able to do this. So you can do this. I'll leave that as an exercise, probably give that in the next homework assignment. You can do this for the case when r or y1 is equal to minus p0 by 2, okay, and you can do this entire exercise for that, and you will get some solution. Okay, you will get t to the power of p naught t, something like that. Okay, good. So that's what the method of reduction of order is about. Let me make sure I don't have anything left out here. No, guess not. And what I'm going to do next is, okay, so we've solved this under all cases, right? When R1, R2 are distinct, we know what to do. When R1, R2 are the same, we know what to do. Reduction of order, you go through this entire exercise. And it doesn't really help to sort of memorize any of these formulae because they're not worth memorizing. You can just go through this entire exercise, put y2 equals nu times y1 and just do what I just did. Just make sure the algebra is correct because it's easy to miss out plus, minus, factors of 1, 2, I do it all the time. So just make sure the algebra is correct and you should be fine. Okay. And so you will be able to solve, under any circumstances, you should be able to solve this. Under any circumstances, you should be able to solve this because we know what to do when you have an f. Same procedure, yp is equal to u1 y1 plus u2 y2, blah blah blah, all the usual stuff, and then you come back, you'll get that integral f y2 by Wronskian, f y1 by Wronskian, whatever. Okay, so this problem is solved. Okay, this problem, both problems are solvable. Okay. In fact, the first problem is exactly solvable and the second problem can be reduced to quadrature, right. So in that hierarchy we had exact solution, quadrature series thing. this guy is right up there. Okay, this is really the best, the least hopeless situation. This is kind of there for certain types of f. You can solve it, you can evaluate that integral, and you can solve it, but it depends on the type of f you have. If you have an arbitrary f, then you can at least do the quadrature integration. You have to just integrate f y2 by Wronskian, f y1 by Wronskian, whatever. Okay, so you can get expressions for both of these. This problem is solved. Good, but the technique that I have described can be a little bit tedious in general. So usually whenever f takes common form, so for instance, teach you, okay, this is the only trick I'm going to teach you. Okay, there's no other trick in this stuff. So usually you can, f of t is of the form, you know, if you're looking at a vibration problem, for instance, it is something like f0 sine omega t or cos omega t or some of the two terms and so on. Or you could have f0 f of t is equal to a plus bt plus ct square, like a polynomial, right? And under circumstances like that, it becomes kind of cumbersome to do the integration. Okay, why is that? Well, the integration to determine those u1s and u2s had stuff like some whatever plus minus whatever f times y2 by Wronskian. So if you have a simple looking, seemingly simple looking thing like this, then you have to basically evaluate, and remember y1 and y2 are like exponential, right? So you seemingly have to evaluate an integral that looks like sine of some omega t times exponential of r1 t divided by exponential of r1 minus r2 times t and so on. Actually, you'll have different values, right? So you'll have, this will also have r1 exponential of r1 plus r2 times t plus r2 exponential t and so on, right? So you have some sine plus, okay, you can take this out and then you can cancel out some stuff, but you will have a sine term with an exponential, and that's a kind of painful integral to do. Okay. In situations like this, you can just take recourse to a simple observation, which is that if f of t is, let's say, of the form a sin omega t plus b cos omega t, if it's of this form, it's a periodic function, it has frequency omega, then the derivatives basically are going to contain terms that have sines and cosines, because you take the first derivative, okay, you can take the first derivative of a sine, you will get a cosine, say first derivative of a cosine, you will get a sine, and so on, right. So no matter what you do, you're always going to get a term that has sines and cosines if you take derivatives of f. Okay. So you sort of expect the same type of behavior to occur in the derivatives of y or yp. Okay. So what you do, instead of going through the entire exercise or doing this variation of parameters, you basically set yp as some a tilde cos omega t plus b tilde sine of omega t. Okay, why is that? Well, because when you do derivatives of yp, and remember yp has to solve 1, you have to look for the particular solution, because in the homogeneous solution right hand side is 0, right, doesn't matter. So when you take derivatives of this guy, you're going to start getting terms like cosine omega t, sine omega t again here, and you take derivatives of that, you will get those terms again here. So presumably if you start with something that has that form, you're going to continue having the same form with some complicated algebraic coefficients adding up. Okay. And so if you do this and you put this in 1 with the right hand side especially that looks like this, some other a and some other b, and you compare coefficients. On both sides. Okay. And what do we mean by that? We mean that you look at all the coefficients of the sine terms on the left and equate that to a. Look at all the coefficients on the cos terms on the left, equate that to b. And why do you have to do that? Because sine and cos are linearly independent. Okay. So when you do that, you will get two equations, one for the coefficient of sine equals a, one for the coefficient of cos equals b. So you will have two equations, you have two unknowns, a tilde, b tilde. Remember, a and b are known, that is the forcing function on the right hand side. So you get two equations for two unknowns, a tilde, b tilde, you can solve. Okay, and so that takes care of that problem. To sort of illustrate the power of this technique, this is called the method of undetermined coefficient. You will see this often. It's a useful trick if you are ever studying vibration problems and you do Fourier transform, or even if you study other problems where you do a transform to get rid of, you're looking at a particular mode, for instance, then this is a very useful technique that you can use. Okay, undetermined coefficients. That's what it's called. Because the coefficients are not determined, right? You have to determine what they are by putting and comparing equations. So let me show you a very simple, well, fairly trivial example of how this works. Let's take d square y by dt square. Let's take a let's do this. Let's take a spring attached to a mass, and then I'm pulling this f of t. Okay. So I have a spring attached, a mass attached via a spring to the roof or to some fixed object, and I'm pulling this with a forcing function, and I want to see what is the amplitude as a function of t. You've probably solved this again, many of you have probably solved this before, and you probably know how to do it, but anyway, we'll just go over it just for completeness sake. Okay. And what do you do? Well, you first write down the governing equation. Okay, this, why would you be interested in this type of a problem? Well, this could be a model for something that is a little bit more complicated. For instance, you could be working on a machine tool, right? Or you could be working on a lathe. And let's say this is a tool, and then you're cutting. Tool is being moved, and you're cutting something. This is, let's say, a workpiece. So tool is going against the workpiece, it's removing material like this. Probably seen this in workshop practice or whatever. This part of the material is being removed out as the tool goes, and let's say the force on the tool is proportional to the thickness of the material you're removing. So reasonable enough, right? If the material is not, well, if the material has undulations like this, then this problem is the same as this problem. If tool has some compliance. Tool presumably also has some damping, but we will not worry about it for now because this makes things a little bit more complicated algebraically, but it's something I'm sure you can work out. If it has undulations, then basically the undulations, because the force is proportional to the thickness is undulating as a function of t, so the force is going to look something like this. And if you want to measure the deflection of the tool or the vibration in the tool, then you will be solving exactly this problem. Okay, so it looks like a trivial problem, but okay, you can use it for something that is practically relevant. Okay. Okay, let's get back to this situation. Okay, you write down the equation of motion. You write d square y by dt square plus k times y. Let's say the spring constant is k, whatever. And this is Newton's second law. This is the restoring force. If you draw a free body diagram of the mass, restoring force because of the spring, and then the forcing term because of the f of t. Looks like this. So you have to solve this equation. Okay, and the homogeneous equation is easy. You just take this equal to 0, you solve it, you will get y is equal to a sine of square root of k by mt plus b cos of square root k by mt, whatever. Now to get the particular solution, let me write down yp is a cos omega t plus b sine omega t. Notice this omega is the same as this omega because I'm looking for that part that follows the forcing, not the transient part that's going to die away, or presumably in this case not die away because we don't have any damping. And if I do that, and just for illustrating this method of undetermined coefficients thing, I just go and do a derivative of this. I will get m omega square with a negative sign times a cos omega t plus b sine omega t plus k times a cos omega t plus b sine omega t that is the left hand side, and then this will be equal to f0 sine omega t. Okay. And so from here you can see directly that there is no cosine term on the right. So the sum of the terms on the left hand side should add to 0, right? And the sum basically is a times k minus m omega square. This is the cosine term, this is the coefficient of the cosine term, so just this. So this entire thing has to be 0. There is no reason why m omega square must be equal to k. Remember, omega is the forcing frequency, not the natural frequency. So there is absolutely no reason why omega should be equal to square root of k by m. So the natural consequence is that a equals 0. Okay. So a is 0. So this term does not exist in the particular solution. Okay. And the second, if you compare the sign coefficient, then you will get f0 is equal to b times k minus m omega square, and you will get b is equal to f0 minus f0 by m omega square minus k. Okay. So the general solution to this problem now is basically y is equal to the particular the homogeneous c1 y1 plus c2 y2, and this is sine square root k by m times t. This is cos square root k by m times t, and the plus the particular solution, which is minus f0 by m omega square minus k sine of omega t. Okay, so this is the amplitude of oscillation that the mass will undergo as it's forced by this type of term. Okay, and you can do this and say, okay, when is the oscillation? These are transients, but in this case they are not transient because they don't die out. There is no damping, so they will also continue to oscillate. And in addition, you will have the superimposed oscillation. So the moment you go, the forcing frequency goes, the moment omega goes closer to square root of k by m, this denominator becomes smaller and smaller, but these two coefficients don't. These two coefficients depend on the initial conditions, which is sort of fixed. Okay, but the closer you go to square root of k by m, this is called the natural frequency, if you haven't seen it before, omega n, natural frequency. As the forcing goes closer and closer to the natural frequency, then the response, the final amplitude, will be dominated by the third term, because the first two terms will be bounded by c1 and c2. Sine maximum value is +1, minimum value is -1, same with cosine. Okay, and the closer you go, this will grow with this third term, and if you're exactly at omega equals omega n, then you will get an infinite amplitude, and that's called resonance. Okay, that's what resonance means. You just force something at the natural frequency, the amplitude goes off to infinity. Okay, and this case, at least, it's a little bit sort of idealized because there's no damping. If you are damping, the amplitude actually gets bounded. You can actually use this same scheme to determine the amplitude in that case and so on. Okay, so same idea. So this scheme is useful in many practical situations where you have functions of this form. You can just directly use this type of substitution, this type of substitution, and compare coefficients and be done. Okay, so that's another thing you want to keep in mind. Okay, good. So that's basically all I have to say about constant coefficient ODEs. They're really the simplest ODEs that we can, simplest linear second order ODEs that we can solve. The only ones we can solve in closed form in any case. And they're quite common, so it's important to be familiar with these techniques to be able to apply them to a wide range of systems, and to be able to do some of this algebra, especially this variation of parameter stuff and the reduction of order stuff. You just have to be careful, but please make sure that you're comfortable with this type of manipulation. Okay, it's just purely algebraic. There is nothing very intellectual about it. It's purely a question of sitting down with a decent amount of paper and working through it. Okay, and once you work through it a couple of times, you will you probably even remember what the final expressions look like. Okay, so let's now ramp up the difficulty. Okay, it's all fine and good if you just sit with second order constant coefficient ODEs, you're not really going to learn much in your life. And so we'll make the situation a little bit more complicated. How do we do that? Well, we'll say, let's go to a case where the coefficients are arbitrary functions. Again, homogeneous. Now the coefficients are arbitrary functions. What is the best we can do in this case? Okay, we've seen that we can't factorize this. I discussed that the last session when we bravely tried to do this factorization into two sequential first order ODEs, and it sort of fell square on its face. So we can't factorize this guy. But what else can we do? The best we can do, it turns out, for any arbitrary P and Q, for any P of t and Q of t, the best we can do is the following. If we are given y1 of t, somebody came to us and gave us one solution, or you could guess the solution from the nature of this ODE. It's possible to do that in some cases, but the differential equation suggests one type of solution already up front. In that case, you have y1, then you can do y2 of t equals nu of t, y1 of t, exactly as we did for the constant coefficient case. You remember, there was nothing there that really assumed that the coefficients were constant. Procedure is the same. You have one unknown, pull back into the equation, you will have one equation for one unknown, you will solve. Okay. So if you do this, you get y2. If you know this, then you can go and do the solution to the homogeneous problem, which is c1y1 plus c2y2. And if you know this, then you can go get the particular solution, u2y2. There is again nothing in this variation of parameter stuff that we did. There was nothing that assumed that the coefficients are constant. The only thing you wanted was linear of this form. Remember, p and q were just there, is multiplied those y prime, y double prime terms and gave them equal to 0. So there is nothing here that assumed that constant coefficients are needed. So you can use that as well. Okay, if you had a right hand side. So this is if RHS equals f of t, you can do this. So if you just know one solution, then you can solve the entire problem for arbitrary p and q. Okay. Again, at the risk of repeating myself multiple times and sounding like a parrot, if you had constant coefficients, if p and q were constant, the problem is completely solvable, completely solved, right? We've just done that. If p and q are not constant, but there are some arbitrary functions, we've seen that we cannot factorize this guy, so it's a little bit complicated. So the next question we ask is, what is the best we can do? And the answer to that question is, the best we can do is, if we know one solution to the homogeneous problem, we can use that one solution, use reduction of order and get the second linearly independent solution. And we can use the second, these two together and get the general solution of this equation. If in addition you had a right hand side f of t term like we had for the other constant coefficient case, then you can do the same thing we did before. Given that you have the solution of the homogeneous problem y1 by 2, you can put yp equals u1 y1 plus u2 by 2 and do the same thing that we did before. Everything will just carry through, okay, no issues. So really the key is in getting one solution, that's all you need. I mean, it's almost there, but it's not quite there, and you can't get there because of that factorization problem. Okay, so that's the beauty of or rather that's the unfortunate situation, because if we knew how to get past this, then you would know that you'll probably be taught that in some undergraduate course or whatever, but you can't get past it. And that's the reason why, depending on the nature of the coefficients, if they obey certain relations, if they're of a certain kind and so on, depending on the nature of those relations, you can actually reduce, you have to look at different techniques specific to certain equations. So there are things called exact equations. Riccati equation we've spoken about before. Something called an exact equation also, which you sometimes will come across, and which you can do certain manipulations to solve, but in general you can't. Okay, so that's basically all you can do. Now what I'll do is and since there is really nothing else you can do apart from doing series solutions, remember that is something that's a sort of hidden hand that we haven't really brought out yet, because turns out you can do series solutions for many of these, for almost all of these problems that you will encounter, and you will encounter quite a few with arbitrary p and q. But when we talk about series solutions, I'll come to that. I'll give you some examples of where these will come from PDEs, reduction to ODEs and things like that. And otherwise there is very little you can do, okay, unless you know one. So there is really no point in continuing this discussion much further. So instead what we'll do is we'll start looking at a geometric picture. Remember the hierarchy, you started with exact solution, we've worked everything out for constant coefficient, only case where you can get exact solution. Then integration quadrature or the series. We said we'll come back to series later, but quadrature we've done. You can reduce everything to quadrature if you know one. It's good. So the next step in the hierarchy of hopelessness is to talk about this approximate solution. Okay, can we say something similar to what we did for the 1D case? What happens when t goes to infinity? What happens when are there fixed points, or are there stable fixed points, unstable fixed points, things of that kind? Okay. Good. So that gives us some hope. So maybe we can say something about this after all. Can't get a solution, just like the 1D case, we decided to forego the idea of a solution and actually come and look at some semi-quantitative things about the solution. So semi-quantitative. Analysis, right? That's the next step. Okay, I'll start this off today and then we'll have to hopefully continue it in the next session. And because if I start going into some of the details, then things will become a little bit complicated and it will take us a little bit of time. So we'll keep it self-contained in the next session. But let's get started first. Remember at the start I said that if you have a probably I should have this printed and stuck on the board or something, I'm writing it all the time. This okay, with the view to generalizing this, let's first generalize. We'll convert this to coupled 1D systems. Okay, how do we do that? Well, we'll just say y is y naught, or y naught is y, y1 is dy by dt, and then we'll see what we can do. We did this, remember, at the start for a third order system. I wrote this down in the first or maybe second session. If you do this, then you will have dy0 by dt is y1, you have dy1 by dt, which is the second derivative, is just this equation. This, okay, so this now becomes a coupled system of two first order equations. Both are linear, of course, but then this one depends on y naught and y naught depends on y1. So you can't just solve them directly as they are. Okay, the first thing to realize is, of course, I think I alluded to this as well at the start. The first thing to realize is now you need two of these conditions, of course, one for this, two first order ODEs, so two conditions. Okay, in all the semi-quantitative stuff we do, we'll assume that these are both initial conditions. The boundary value problem is a little bit more complicated to do analysis like this, but so we won't do it in this class, but we may do it at a later point. But for now, we'll assume that both are. So we're only talking about initial value problems. Okay, and so that means you specify y0 at t equals c naught, and you specify y1 at t equals t naught, t equals t naught or 0 or whatever, right? Okay, so the system now has two axes. You have y naught on the x-axis, horizontal axis, and y1 on the vertical axis. And by specifying the initial conditions, you're basically specifying the coordinates of a point. Okay, so this becomes now our phase space, or a phase now plane. It's a 2D phase space because you have second order system. And the initial condition basically specify the coordinates of a point. Okay. So if I say t equals t naught, y equals let's say this is capital A, this is capital B. Okay. So t equals t naught, capital A, capital B. Okay, specify the initial condition, t equals t naught. So I start here. Now the question of solving the equation, determining the actual solution y is equal to y of t, is a question of now finding out the trajectory that the system undergoes starting from this point. This is the initial point, and this is y of t. Okay, the trajectory. Well, the trajectory is in the plane, of course. It's two dimensional because I've already written y naught and y1. So the trajectory is not just y of t, but it's actually y of t and dy by dt of t. Because if the system starts from here, it's going to evolve arbitrarily in time, presumably arbitrarily. Linear systems don't do that, but okay, whatever. It's going to evolve in time, and the evolution traces a path in this phase space. And the path is determined not just by y, the solution, but by y and dy by dt. Why is that? Well, because the initial conditions had 2 degrees of freedom, a and b, and the trajectory also has 2 degrees of freedom, y and dy by dt, just like this. Okay. So the phase space now has not just y, but y and dy by dt. Okay, it's an important thing to keep in mind. Please keep that in mind. In the first order system, you didn't have the dy by dt, you only had dy, and so trajectory was determined only by y of t. Okay, that's an important point. Now, if I go back and look at the constant coefficient case, let's do the constant coefficient case. Okay, let's look at the same picture with the constant coefficient case. So if I put p of t equals p naught and q of t is q naught, then what happens? The y of t that we found, e power r1 t, e power r2 t, and so on, are basically determined by p naught and q naught. Okay, so minus p naught by 2 plus or minus whatever, p naught square minus 4 q naught, whatever, that quadratic formula, right? If you look at that in this context, so let's take p of t is p naught, q of t is q naught. What will you get? You will get p naught here, y1 is q naught times y naught. This is y1, this is y naught. Okay. So now you have this system. The system can be written in a matrix form. I think we did this also at the start. So this will give you 1, 0. Get rid of this. 1, 0, minus q0 minus p0. Okay, and this is like d by dt of y bar is equal to some matrix M times y bar. Okay, we've reduced our constant coefficient. Remember, this constant coefficients. The reason will be clear a little bit later. But the constant coefficient system we have reduced to this system of first order ODEs. Now remember, when we did this first order ODE stuff in phase space, we drew phase space. Of course, that was the first thing we did. And the second thing we did was find the fixed points. And what are fixed points? Fixed points are where you start. If you start exactly at the fixed point, you will stay there forever, right? That's how we define them. And how do we define it for the 1D case? Let's see, first is 1D, where you have dy by dt is some f of y. This is the autonomous 1D case. We said that the f of y star is equal to 0. Okay, and so the left hand side derivative was equal to 0, and then okay, you just stayed there if you started there. Okay. Now you can take the same idea and extend it to this. Okay, so you have m times y is equal to 0. Now that will become a fixed point. But now you have two equations, because you have one here and you have one here, and you have to solve them simultaneously because you have two variables on the left hand side, not just one. Notice how the dimensionality is coming in through the order by changing this, by doing this. Okay, so you have two simultaneous equations for two unknowns. So the fixed point is a point in this plane which has two coordinates because it's in a plane, and the two coordinates are obtained by solving this system. For this case, okay, it's fairly trivial, because if you look at a fixed point, then dy0 by dt is equal to dy1 by dt is equal to 0. So the first one will give you y0 is equal to 0. Second one will give you y1 is equal to 0. Okay, fixed point is at the origin. For a linear system, constant coefficients, the fixed point is at the origin. Okay. So we're trying to do the analog of what we did for the first order system. Now we can presumably start doing the same thing we did last time. We can start talking about stability of these fixed points. What happens to these fixed points if there's a parameter in the problem? For instance, I could increase the mass or lower the spring constant, things like that. Now you start seeing those possibilities. I can change the natural frequency. And you can ask the question, what happens if I do all of that stuff? Will the fixed points be the same? Will they move around? Will they change their stability and so on? That's stuff you can ask, right? And not only that, now the situation becomes a little bit more complicated. Remember at the start I had said that in the first order system you cannot have oscillations, right? If you have autonomous first order system, you have a fixed point here, and if you start from here, you're going to reach the fixed point if it's stable, you're going to go away from it if it's unstable. So eventually you'll go away, you won't come back to the original point, right? We discussed this. You can't have oscillations. Autonomous first order system. Okay. But now you can start here, presumably in some general case, not this linear case, but in the general nonlinear case, you can start here, and instead of coming here, you can go out like this. Okay. And if you go out, you can just go about like this, and come back to the starting point. Without actually going through, without being constrained to this line, you can go around this point. So now second order systems will start showing oscillations. Okay, and that's also the reason why if you have a spring mass damper system, the oscillation term comes from the inertial term, the md square y by d square, because of dt square, because that is the second order term, and second order terms can show these oscillations. We'll see details of these later, but at least conceptually this idea should be clear. The inertia term is responsible for the oscillations, which is why if you go back to the simple situation we had worked out, the d square y by d square minus y equals plus y is equal to f of t, we had worked this out, right? This homogeneous system is what we're looking at now. We'll just forget about f because we're looking at a homogeneous system. This will show oscillations. No bound, it's not damped oscillation, it's undamped. And so the reason it's undamped is because of this term, the second order term. That's the one that's responsible for the oscillations. The damping term wants to get rid of the oscillations, and that's why it has to be proportional to dy by dt, because dy by dt is a first order term, and the first order term basically wants to go towards a fixed point. Just like the 1D case, dy by dt was the only term you had in the 1D case. Okay, so there's a reason why there's a very deep reason, at least geometrically deep reason, why damped oscillatory system must have a second derivative term. If it's damped, it must have a first derivative term, and the third term is just proportional to this, which is the spring constant term. Okay, you will in practical situations also come across things that are called over-damped oscillators or under-damped oscillators. This means that the coefficient of this term, the under-damped case, coefficient of this term is much larger than the coefficient of the damping term, the first order term. or the over damped case is the coefficient of this term is much smaller than the coefficient of the damping case. So the first order nature of the situation takes precedence over the second order nature. Okay, so that's why you will see either things that is oscillating over short time or long time, but stuff that is also decaying towards the origin. That's the origin, physical origin of where the stuff comes from. Okay. Good. So I think we know what this phase space stuff. At least we know what phase space looks like for a start. We know that it has 2 coordinates. It needs 2 of these conditions and so on. What we'll do next is we will start working out the general case. Okay. So just like we did for autonomous first order systems like this, we will look mainly at autonomous second order but non-linear systems. Okay. There is very little we can do with stuff when you have coefficients depending on t. We'll look at autonomous non-linear systems, construct phase space for that, and then we'll start looking at what is the equivalent of the linearization scheme that we did for the 1D case. Okay. And then based on that we can classify fixed points, we can see how fixed points move and so on. We can do all the bifurcation stuff that we did before. Okay. So that's where we'll start off in the next session.